Testing. Hi, everyone. Just needed to turn on the power. Important for data centers, too. So my name's Holzle, and I lead the technical infrastructure team at Google. And I'm going to talk to you a little bit about both the past and the future of our infrastructure. At Google, I've worked on infrastructure since 1999, so over 15 years. And back then, we already had a pretty simple homepage, not quite simple enough, but we had a huge infrastructure problem. And we had a huge infrastructure problem because search as an application is incredibly compute intensive, right? You search all the world's web pages in a fraction of a second, right? That actually needs a lot of hardware. But back in 1999, servers were very expensive. Linux was barely working. Our web servers would crash every few hours because of bugs in the network stack and in the kernel. And so this wasn't actually very easy. You didn't have public clouds. You barely had data centers. Colocation was invented 3 years before. So we had a big infrastructure problem, and of course we had no money. So what did we do? Well, the first thing we did was try and make the computation itself cheaper. And so we built, and then I forgot to say, exactly the other problem, of course, not really a problem, is that we had traffic growth by a lot. So here is an example of the actual, in the upper right, you see the actual crayon graph that we had on our wall and the stylized version in the slide. This is a period of 5 months where our traffic grew by a factor of 10, right? And remember, this was a company with 7 people or so at the time. And by the way, if you're an infrastructure person, or actually even if you're not, if you see a graph like this and it's as jagged as this, you have a real problem, because it means you have very likely bad availability or bad performance, because real user traffic doesn't vary like that. And your diagnosis would be correct on both counts back then in 1999. It typically took 3.5 seconds to answer a search if we could answer it. And typically at noon every day we couldn't, because we were overloaded. So what did we do? Well, we tried to build cheaper servers. Here's one example of the series that we built in 1999. So our first 2,000 servers basically looked like this. And actually, amazingly, it kind of worked. We had a bunch of other attempts at building hardware, and the goal really was to go and build a reliable infrastructure out of relatively unreliable parts. And recall that Linux really just barely worked, and if you see our hardware designs, then you know that we were in early stages there too. Now, a little bit later, it looked somewhat cleaner. So here's a picture from 2 years afterwards. But even at that scale, you really need to be able to deal with failure, because imagine you bought the best servers in the world, and they fail only every 10 years, right? And basically nobody can build that servers, but let's just assume you could, right? 10 years is 10,000 days, it's 3,000 days. So that means once you have 3,000 servers, probably one of them is going to fail every day. And you have 30,000 servers, 10 of them are going to fail every day. So you really have to get good at handling failure. And once you're good at it, it doesn't really matter whether 10 or 100 of them are failing every day, as long as it's a small percentage of the overall. So back then, everything was really just a struggle to survive. But as soon as we had a little bit more time on our hands, we tried to rethink things from top to bottom, because we weren't happy with what we had. And search is really the thing that forced us to change everything. Because as I mentioned, it's so large that you can't really solve it in a conventional way. So we didn't have an alternative. We were forced to parallelize everything and to build new kinds of hardware and software to support applications like that. So one of the things I told you was, hey, you have to be good at handling failure, but that's really just one of the things. So let me walk you through a few others. This is a timeline of sort of major systems that we built and talked about publicly. So almost all of these things have technical papers published, and with a good search engine, I'm sure you can find them. The first thing you'll note is that nothing on this map is kind of before 2003. And that was really because until something like 2002, we were in survival mode. We couldn't really think of doing something ambitious that didn't have immediate payback. And so that's what you see here. The very first thing was GFS on the lower left, stands for Google File System. That is a file system that we built to store very large amounts of data on disks throughout a cluster. And the basic idea was that you take your data, you chop it up into parts, and then you place these parts onto different disks and different servers, so that if ever a server fails or a disk fails, you still have a replication of that block somewhere else. And in the background, once the server failed, something goes off, figures out which parts were on that, and replicates these blocks, so you're back in a state where you can tolerate the next failure. And the first thing we used this file system for was to build a larger web index. So the first user was our crawl and indexing system that takes all the web pages and builds an index that is searchable. And that was a key thing, a key system that allowed us to have a much more comprehensive search index, so a web search with many more documents in it than our competitors, because we actually had a way to use tens of thousands of disks and automatically deal with all the failures. The next thing that came pretty shortly afterwards was MapReduce. MapReduce in red on the left too is a way to formulate a computation and then run it on 1,000 or 10,000 servers and 10,000 or 100,000 disks without really knowing much about parallelism. So you may have tried it yourself. Hadoop has a public implementation of MapReduce today. So it was really the first system back then that would allow you to have a relatively simple specification and then run it at really large scale. And the system deals with failures and figuring out which data is where and how to parallelize it, etc. That wasn't your problem, that was the system's problem. First use, you won't be surprised, was to build our web index. This made it possible for us to have much less code to rebuild our index from the original pages. So our indexing system basically became a huge a set of MapReduces that was much simpler to evolve than our previous system that tried to do this all by hand. And that was one of the reasons why, as a company, as a search engine, we could introduce new quality improvements much faster than the competition, because we had a much more manageable code base. After that, the next major system was BigTable. BigTable started the NoSQL movement. Today, you might know it as HBase, Hadoop HBase. NoSQL is really about storing very large amounts of data that are kind of structured, but not structured the way you would structure them in a typical SQL database, and also at much larger scale, so that regular SQL databases just can't handle the volume. So we built BigTable, which really pioneered the NoSQL ecosystem. And surprise, surprise, the first thing we did with it was to use it for web search indexing. This was the system that allowed us to keep the state of what we know about the web, all these web pages, in a database rather than a bunch of files. And that allowed us to make our indexing continuous rather than batch. Until we had BigTable, our indexing was kind of every day, every week, you ran giant MapReduces to create the next index, and then you rolled it out. But so you had a long latency between index refreshes, and with BigTable, we kept all of that state in a BigTable database, giant BigTable partition. And then that allowed us to really update the index every day or even every hour or every minute. There's many others here. For example, Colossus replaced GFS, so we're not actually using the Google file system anymore. Colossus is our successor that today stores pretty much all of our bytes, including all of our bytes in our cloud system. Spanner, to some extent, is a successor to BigTable with much nicer semantics. MapReduce, we don't actually use anymore internally. We now use something that externally we call Cloud Data Flow. That makes it possible for you to build systems that are composed of many MapReduces in a much more natural way. There's a few green boxes here, and I'll talk a little bit more about them later. That's our hardware efforts, because it was obviously important not just to make software good, but also to make our hardware more efficient. The very first one we did was efficient power supplies for servers. That was a very localized change, but back then servers were incredibly inefficient, and they wasted on the order of 40% of their power before it even got to the motherboard. So that was one of the things we fixed very early on, because at Google all the builds were coming into one place, and we quickly realized that we were paying way too much for electricity, and for a few dollars per server we could get rid of 40% of the electricity cost. So many of these innovations have found their way into open source. Here's just a few of these systems that come out of either ideas or code from Google. And one of the things that I think is often underestimated is that the public clouds have really amplified the impact and the importance of open source. And conversely, open source has amplified and enlarged the impact of public clouds. Because it's really easy for you to take open source packages and stand up your own infrastructure on a public cloud. So now let's go a little bit. Oh, and by the way, before I go to hardware, beyond this, of course, we've done a lot more in the open source ecosystem. In Linux, for example, back in something like 2007, we put in the kernel modifications that allows containers to run as partitions in Linux. C groups, it was called at the time. So that's actually what Docker images run on today on Linux. We wrote this a long time ago because we needed it internally, without Docker, but with our internal equivalent there. Or last year, for example, we found the hard split bug in OpenSSL, because we're a heavy user of OpenSSL, and so we're looking at that code all the time. But now let's go to fun stuff like hardware. Obviously, we have to rethink really how the data center worked, and I have only a minute and a half to talk about it, so I'll just show you a few things. Here's the example of racks that we built. On the right-hand side, you see it on a shaker table. It kind of simulates transportation and earthquakes to make sure that it doesn't fall apart. We had container data centers. In 2005, we deployed our first container data centers, where we pre-provisioned containers with servers inside and basically rolled them into a warehouse. It was a very quick way to get up to speed. It also probably was the first data center that had less than 20% overhead for cooling and UPS. We continued that, tried a lot of new things, all of which worked, cross your fingers. For example, the first chillerless data center, meaning the first data center that doesn't have mechanical cooling, was built in Belgium in 2007. First seawater cooled data center in Finland in 2009-ish, can't remember exactly. And today, just as what we were thinking about, not individual servers, but groups of servers, way back when, and then not just individual racks, but group of racks, today actually we think it's data centers not as individual buildings, but as campuses with multiple buildings, and how to manage really the assembly of those buildings as a unit, rather than just the individual building. This is a picture of Belgium. So today, as an infrastructure person, I like to say that Google is an infrastructure company with a great UI, right? And the UI is expressed in the products that you all know. And the new UI is a Google Cloud Platform, where we're exposing all of that infrastructure, and it's really the same infrastructure that internal teams use to everyone who wants to as part of Google Cloud Platform. Let me just show you how we're different there, and I'll walk you through 3 examples. I mentioned containers already, but the traditional way of running your application in a cloud is VMs, right? So you pick up your application, you create a VM image, etc. Works great, probably an improvement over what came before, but it doesn't really work that nicely. It gets in the way between your application and the hardware. And so at Google, we never used virtual machines inside. But we use something that today is called containers. We call it something else. But the idea with containers is that you package up everything that belongs to your application, and then you hand it to a cluster manager, and the cluster manager runs that application for you. So now you don't have to worry about OS images, security patches, how many of these different parts of your application should run on the same machine or on a different machine, what machine type you should use, et cetera, et cetera. So a whole class of administrative tasks kind of disappeared, right? So that's what you can have today at Google. Kubernetes. Our cluster manager is fully open source, and we have a hosted version of that as well. It's really a much simpler way to run your applications and think about your applications rather than thinking about machines. On the data side, I mentioned data flow briefly. So data flow allows you to, in just a few lines of code, write a data pipeline, right? From cleaning your data to reducing it, maybe to aggregating it, to doing transformations, whatever. And then the system worries about how to implement this pipeline as a computation. And you have two choices. You can implement that pipeline as a batch pipeline where you read from a data source, could be BigTable, could be a storage system, and you run it as a batch, highly efficient, highly optimized, typically substantially more efficient than what you could do with MapReduce, because the system, seeing the structure of your pipeline, actually can fuse different MapReduces together to eliminate temporary copies and things like that. Or you can choose to run it real time when you point it at a streaming data source, and then you get updates every 5 seconds or whatever of whatever your outputs are. So again, much simpler way. You don't have to set up a cluster. You just express your computation, and then you point it at the inputs, and you say run. And then finally, we think that in a real cloud, what you actually want is flexibility. And so it doesn't make sense to port pricing models that come from the on-premise world into the cloud. So we don't have contracts or commitments or penalties when you change your VM type. We have per minute billing, right? You don't have to pay per hour or per year. And we give you automatic discounts if your workload is flat, because we can implement that workload more cheaply. Whereas if your workload is very spiky, we actually have to have more hardware there, so it's more expensive. But the base price is here, and then every month you automatically get discounts if your actual load profile is flat. So long term, let me talk about just one more thing that actually isn't very big today in the cloud, and that's security and compliance. So today, obviously, a public cloud is a great choice for economic reasons and for technical reasons. But to be really successful, for cloud to address, let's say, 50% of the world's workloads, server-side workloads, it also needs to be the best solution for anything else. So that includes security and compliance. And so that is something I think that over the next few years, people will really realize actually is one of the key reasons to choose a cloud. Today, often the gut reaction is to say, oh, like my data is in someone else's data center or on someone else's infrastructure. That's got to be less secure than me having it in my building. And I think pretty soon, people will realize that isn't quite true. And in fact, there are lots of companies who already have painfully realized, and it's not because they did a bad job. It's because it's actually very, very hard to have a secure stack and use it correctly and have an application or a general surface, attack surface that actually can hold up to the kind of attacks that are out there today. And at Google, we are obviously a target too for all kinds of shenanigans. But over the years, we really learned how to deal with that. We have a very good security team, and we can afford to have a 500-person security and compliance team and privacy team to actually build all these mechanisms, all this monitoring, et cetera, because amortized over our scale, that's actually not very expensive. Most other companies can't do that. And so as we externalize all of these features into our cloud, it's possible for you to run at a security and compliance level that's approximating Google without spending 500 people yourself. So I think one day this will be very big, and one day it could actually be that if you're working for a larger company, that your auditor is flagging an in-house application as a security risk. Because everyone knows, quote unquote, that GCP stack is secure and certified out the wazoo, whereas yours is kind of homegrown, so that is an unnecessary business risk. We're not there yet, but you will be there before long. So just to wrap up, we've been out there for a long time, and I think we're actually at the very, very beginning of cloud. Everyone talks about cloud, and it kind of feels, and probably you are all in the early adopter crowd, so it feels very natural, like, of course everyone is doing it. Actually, everyone is not doing it, right? The vast majority of cycles out there in the world are not in any cloud. So that revolution is still happening. And also, in the grand picture of where the cloud will end up, we are very, very early. I like to compare that to cell phones. And I think in cloud, we are where cell phones are in January 2007, right? You actually have very nice, Nokia feature phones, but the smartphone hasn't been invented yet. And if you go from January 2007 to January 2012, and you took your January 2012 phone, and you looked at it and said, these are the 5 things I really love about my phone, right? None of these 5 things were present in the 2007 phone, right? And so I predict that in 5 years from now, you look at your cloud and you say, these are the 5 things I really love about my cloud. None of these are going to be present in a cloud today, even though you may see a few things in data flow or containers that you can recognize as early primitive forms of what you really love in 2020. So with that, thanks very much for your attention, and go use our cloud.